Okay. So we had this thing called the strong principle of equivalence, and it says that laws of physics are the same in a uniformly accelerated frame as it is in a uniform gravitational field. In other words, we can replace the gravitational field, a uniform gravitational field, by a coordinate transformation. Remember that this is only for uniform gravitational field, but in realistic gravitational field are never uniform. They are either converging or diverging, but I can take a sufficiently small region of space and conduct an experiment for sufficiently short time that I can make it in that infinitesimal region. I can consider the gravitation to be uniform. And in that local region, I can replace it by a coordinate transformation of an accelerated frame. Geometrically, it is just like if you have a smooth surface, at any point, I can draw a tangent plane and at a sufficiently small region around the point of contact, the surface can be approximated to the tangent plane. So this is the geometric manifestation of the fact that I can take a locally flat space-time. Is this clear?
Yeah.
Yes.
Okay. Now, so when I say laws, I mean all the laws and not just mechanics. And when I say the word same or the same, what I mean is it has the same mathematical form. Okay. Hi, Anirudh. I just recapitulating something on strong equivalence principle. Okay. So this is the strong equivalence principle. Now, what is the mathematical? It says equation of the form LHS is equal to RHS. And if I make a transformation, then LHS goes to LHS prime. Under this transformation, RHS goes to RHS prime. RHS prime. So from LHS has become like this, RHS has become like this. Now, in this unprimed frame, they are same. The question is, what happens in the primed frame? The equivalence principle demands that even in the primed frame, these two are same. In other words, if LHS equal to RHS in one frame, the transformed quantities on both sides should also be equal in the new frame. And this is the central point why tensors are used in order to study general relativity. Now, what is the implication for mathematical formalism? It says that only those mathematical equations with such properties can represent physically relevant laws, which is sort of understandable because I keep telling people that if a person jumps from the 14th floor, the person falls and dies, whether you describe it in Cartesian coordinate or polar coordinate. So a physical reality cannot be dependent on what coordinate system I use. So in other words, any physically relevant law should be coordinate independent, and hence it should have this property that its form should be independent of which coordinate system I use. As we will shortly see, certain mathematical quantities follow such properties, and these mathematical quantities are called tensors. And that is the motivation why we are going to take a digression and study in detail about tensors, because that is the fundamental mathematical pillar on which general relativity is built. Okay, can I proceed now? Is the basic philosophy clear?
Can you explain to me? I think I missed a little bit of it.
No. Basically, what I was saying was, the strong equivalence principle says that laws of physics are same in a uniformly accelerated frame as it is in a uniform gravitational field, which I told last time.
Okay. Yeah, okay.
Okay. Now, I also said that in reality, you don't have uniform gravitational field. However, if you take a sufficiently small region of space-time, so a local region of space, and observe for a sufficiently small amount of time, you can approximate this to a uniform gravitational field. And hence, I can replace it by an accelerated frame. However, if I go from one time to another, I will have to go to a different accelerated frame. It is something like, suppose I have a surface which is smooth, but ups and downs. At one point, if I take, I can always draw a tangent plane to that surface. And around the point of contact, I can approximate the surface to the tangent plane. However, if I go to another point on the surface, it is another tangent place which I have to take. So this is just the space-time manifestation of this, that if I have a realistic gravity, since the gravity is not uniform, at different points in space and at different epochs of time, I will have to construct a different uniformly accelerated frame with which I can identify the gravity in that local region.
Okay.
Okay.
Got
Right?
it.
So, and one thing which you need to remember is, when I say laws, I mean all laws and not just mechanics. Because if it is mechanics, that, as I mentioned, it was a weak equivalence principle. Since it is all laws, this was the hypothesis of Einstein. While mechanical, this weak equivalence principle was as a result of experiment which Galileo did. Equivalence principle was a hypothesis by Einstein motivated by this. That is the important difference. And when I say same, the laws are the same, it means they have the same mathematical form. And so, as I was saying, any law can be expressed as two quantities, LHS and RHS, which are equal. Now, if I make a transformation, LHS goes to LHS prime, RHS goes to RHS prime. The strong equivalence principle demands that even in the primed frame, these two are same. And so according to strong equivalence principle, LHS equal to RHS should imply LHS prime equal to RHS prime. And this is, so I have to construct a mathematical structure for general relativity which obeys these equations. Okay. Anirudh, is it okay?
Yeah, it's clear. Thank
Okay.
you.
Now, what is the implication for this mathematical formalism? It means that only mathematical equation with such properties can represent physically relevant laws. And what are the mathematical quantities which have such properties? These are called tensors. And that is why tensor is very central to studying general relativity. Now, while studying tensor, I'll do a brief recap of scalars also, which I already did, but very briefly so that there is a continuity. So we will have scalars, vectors, and tensors. Now, as I was mentioning earlier, what are scalars? Now, suppose phi is a function defined at every point in space-time. Okay. Now, the space-time itself may be described by different coordinate systems. For example, it can be polar, it can be cylindrical or whatever. So similarly, space-time, I can always, so what is it which is happening when I'm going from one transformation, one coordinate system to another? I mix up the coordinate systems to produce new set of coordinates. Now, if I mix up with time also, it is basically space-time transformation. So the space-time itself may be described by different coordinate systems. And accordingly, there is P. That is, what is the position of P will depend on the coordinate system, whether it is polar, whether it is r theta phi or xyz. Is it okay?
Yeah.
Okay. In general, I will have two systems, T, X, Y, Z. Sorry, I mean, I actually meant this is actually and okay, T, X, Y, Z and T prime X, Y, Z, or in short, I will call Xi and Xi prime. Now, I will use the Latin indices, which is I, J, K, and so on, for indicating space-time coordinates. That is, they will go from 0 to 3, time X, Y, Z. Whereas if I use a Greek symbol, these indices will indicate only spatial coordinates. So this is the general convention which I will be following throughout these lectures. Now, a physical quantity, okay, the functional form of the physical quantity depends on the coordinate system I use. So the functional form of any physical quantity, which I'll give examples, may be called phi and phi prime. There are two different functional forms. However, the value of the quantity is the same independent of which coordinate system it is described in. So you need, so as I have been emphasizing, you have to distinguish between functional form of the form of a function and the value of the function. Okay. The value of the quantity in the unprimed system at point P is phi of P, which is, I call it phi of xi because I am describing P in the unprimed coordinate system. The value of the quantity in the primed coordinate system is phi prime of P because the P physical quantity is the same whatever be coordinate system, but its description in terms of coordinates will be different in the primed system. So here it will be phi of x, here it will be phi prime of x prime. Now, if this quantity is a scalar, what you need to do have is phi at x should be equal to phi prime at x prime. Or alternatively, you can just write that phi at P should be equal to phi prime at P. That is, at the physical point P, the value of phi, the physical quantity, should not be different depending on the coordinate system I use. And the example which I gave was an example of distance. Now, I consider the distance, a point P, and the distance of the point P from the origin. In the first coordinate system, I use Cartesian P of xyz. And the distance, which I call phi of xyz, is x squared plus y squared plus z squared. And this I call as x1 square plus x2 square plus x3 square. Okay. I have another system, which is cylindrical coordinate system, where I call it rho, phi, and z. Rho is the distance in the xy plane. Phi is the azimuthal angle along the xy plane. Z is the z axis. Now, the distance here, the coordinates now are different, and the form of the function, how it depends on the argument, is different. Here, it takes the square of the first one, the square of the last one, and 0 times the square of the second one. So this is what I said, that the functional form is different. However, so phi acts on its arguments, which is different from how phi prime acts on its own arguments, which is x prime. But same for P, independent of what coordinate system I use. I had emphasized this earlier in one of the lectures, but I just want to make sure that it is understood. Is it okay?
Yes, yes.
Okay. I mean, the important thing is the form of the function is not same. It is the value of the function which is same. Another example we can take is that of the length of a rod. Now, the length of the rod does not change under rotation. So if I have a rotation, x prime, y prime, z prime, and the rotation is in the xy axis. I have cos theta, sin theta, minus theta, cos theta, 0, 1, x. Then the length remains same in both the coordinate systems. Okay? Now, as I was telling earlier, is a scalar for all transformations? The answer is no, almost never. And as an example, let us consider the length of the rod. The length of a rod remains same under rotation. So if I take something and rotate the coordinate system, length of the rod, but it changes under Lorentz transformation. So a length of a rod is a scalar under rotation, not under Lorentz transformation. Similarly, if I take the projection of the rod on the x-axis, it remains same under rotation in the xy rotation, but it changes under the xz plane rotation. So the z projection of the rod is scalar under xy rotation, but not so under the xz rotation. Am I clear?
Yes.
Anil?
Yes.
Okay.
Yes.
Okay. Okay. So, as I was mentioning again earlier, when somebody, if we say, is something a scalar, is a wrong question. The right question is, does so and so quantity behave as a scalar under a given transformation? That is the correct question to be asked. Okay. Now, for example, in this whole thing, the length of the rod is a projection of the four-dimensional length on the space. So just like Z projection in 3D space, basically the length of the rod is a spatial projection in space-time. Okay? And that is why it doesn't remain same transform time and do Lorentz transformation. So are scalars clear? Now we'll go over to vectors and tensors.
Yeah.
Okay? Yeah? Now let us come to vectors. Their value, see, I told in scalar what happens. At a physical point, their value remains same. But in vectors, their value, even at the given physical point, is not the same. Because when calculating the components of a vector, necessarily the nature of coordinates comes in. Okay. So their value, even at a given physical point, is different from different coordinate systems. And the value, even at the same physical point, changes under the coordinate system. So see, in the case of phi, I said only form of the function changes, but the value doesn't change. Here, even the value changes of the components. To be classified as a vector or a tensor, or what type of a vector or tensor, depends on how this change happens when you go from one coordinate system to another. All right. Now let us talk about vectors to begin with. Here, suppose I have a system in a transformation where I go from xi to x prime I. Now, x prime I, it basically means any coordinate transformation, the new coordinates are just so many functions of the old one. For example, suppose I have x, y, z, and then r, theta, phi. Then r is a function of x, y, z. Theta is a function of x, y, z in general. And phi is a function of x, y, z. So when you say coordinate transformation, I just mean that I have considered, if there is then a coordinate transformation means I have considered a set of n independent functions which are alternative coordinates with which the space-time can be described. Is it clear? Yes? No?
Yes.
Okay. So now, when I do this means that every xj here is a function fj of all the coordinates xi's. Okay, so basically this is what it is. which means that if I take a dx prime j, I mean, I'm just repeating a few of this so that I have continuity with the tensors. So if I have a differential of this primed coordinate system, from the theory of partial differentiation, I know that it is del f j, the jth function, because corresponding to this, derivative with respect to xi, dxi, and the repeated indices are summed over. Okay, so I will mention this. Okay, so there is a summation on I, and since fj is same as x prime j, I call this in this form. Now, suppose we have a one index object that is in space time, since I have 4 values of I and 4 values of j. Suppose I have an object which has 4 components, and each component, the ith component, I am calling by ai. And when the ith component transforms in the way dx transforms, I call these as contravariant vectors. And more precisely, AIs are components of a contravariant vector, which basically means here that I need to have screen. So basically it means exactly like x prime, a prime j is equal to del x prime j by del xi ai and summed over I. Quantities which transform like this are called components of a contravariant vector. Now, again, I repeat, often, even in some of the interviews, people ask, is velocity a vector? Rubbish. The question is, does it behave like a vector under some transformation? Okay. 3 velocity is a vector under 3-dimensional coordinate transformation. It is not a vector under Lorentz transformation. Okay. So far clear?
Yes. Yes.
Okay. Now let us come to one more type of vectors. Okay. And for this, let me look at it this way. Suppose I start with the scalar. I told that scalar have this property. Phi of x is phi prime of x prime. And I will take the del by del x prime, the partial derivative of this. Okay. Which is equal to this. So this is operating on phi prime. And again, from theory of partial differentiation, I can split this like this. And I will just put this in front and I will get xj by x prime I, del by del x prime, del by del xj, phi prime x prime. But phi prime x prime is same as phi x. So it is del xj by del x prime I, del by del xj of phi x. Okay. And here, this, since phi prime is same as phi prime x prime is same as phi of x, I can write this as del by del x prime j phi of x. So what does it say? It says that del by del x prime j acts on phi and produces this which acts on phi. Okay. And so I have del xi by del phi will be equal to, so by del phi is equal to, sorry, Yeah. So this will be equal to this thing. I mean, this is the thing which will be there. That is, del by del xi will be del x prime j by del xi, del by del x prime j. And so this is the operator with which, I mean, maybe I have interchanged prime and unprimed in between. So you just check it up. Okay. This is just the partial differentiation ka definition. Now, just like I said that if I have a one index object, AI, which is transformed like this, a contravariant vector. If I have a one index object, BI, which transforms the way this transforms or this transforms, namely like this, then I call this a covariant, sorry, vector. That is, so by convention, for contravariant vector, I will put the index on top, and for covariant vector, I will put index on the bottom. Now you contrast this in the following way. You see here, when I had the contravariant index up, then it was, it was unprimed. So it was unprimed contravariant is unprimed by primed. Here it is primed by unprimed when the index is down. You understand this?
Yeah.
Okay. So this is the difference between the two kinds of vectors. I will just mention one thing without calculating. Maybe at some time I will do, just to give you a flavor of what it is. Just let it move like this. Now, suppose I have a coordinate system which is not orthogonal. Suppose the coordinate system in which y and z are at an angle. And I have a point P here. And I have a position vector which I call V or R or whatever. I can make two kinds of projections. One is I can drop a perpendicular from P to this axis and a perpendicular from P to this axis and call this A1 and A2 as the two components of this vector. Okay. I can alternatively, I can actually draw a line parallel to this, another line parallel to this, and get another two components, B1 and B2. Now, in the normal thing, when the axes are perpendicular, both will be the same. That is why you did not have to make this distinction normally when you do Cartesian system. But the moment you have this, these two components are the ones which are just mentioned. The ones which are got by perpendicular component are contravariant vector components. And the ones which are got by drawing parallel is covariant component. So I write the A1, I call it V1 upper 1 because it is contravariant. A2, V upper 2, it's contravariant component. B1 as lower 1 covariant, B2 as lower 1 covariant. Is this okay?
Yeah, yes, yes.
Okay. Now, in order to understand why this is so, there is one thing exercise you may try, that you rotate this system by a certain angle theta and see how the coordinates transform. And you should be able to get these things. Okay. I will give problems and all in this, but right now I wanted to cover certain ground before we do something. Okay. Now I'll come to what are tensors. Now, if we have vectors, can tensors be far away is the one which I generally say, because it's basically a generalization of vectors. And in this, let me consider one case in which I will construct this two index object. Previously, I had one index object. I construct this two index object, which I can call a matrix, in which the first index is this one, and then this one. So it's a Cij is a product of the ith component of A with the jth component of B. And here both are contravariant, both A and B. Now suppose I go from prime to a barred frame. I just put a barred instead of prime because there is a number of indices go on in this confusion. Since this is contravariant, how will it go? It will be A bar k is equal to del x bar k by del xi. See, bar is coming because it's a contravariant into ai. Summed over I goes without saying. Similarly, I have b bar l is equal to del x bar l by del xj bj, again summed over j. And now I multiply both sides. I get del x bar k by del xi into del x bar l by del xj into ai aj. So these two all are multiplied. Ai bj. And the right hand side is basically a bar k into b bar l. And so this quantity is just the Cij. And this quantity is another two index quantity in the new coordinate system, which is C bar KL. And so you see that the C bar KL transforms in this way. So you see that each index transforms as if it is a covariant or a contravariant vector. Here both are contravariant. So you have a bar up in both. Is this clear?
Yeah.
Yes.
Yes, yes.
Okay. Now the objects that transform the way Cij does, that is the way the product of AIBJ transform, they are called second rank contravariant tensor because both the indices behave like contravariant indices. I can actually now do the same thing, and I leave it as an exercise, in which I construct a two-index quantity Dij, which is covariant AI multiplied by covariant Bj. And here, if I do the same thing, I will find out this. Here you see that in this case, when K and L were up, then bar, unbar, bar, unbar. Here unbar, bar, unbar, bar. That is the difference. And these are called second rank covariant tensors, just like you had covariant vectors. Now, once you have tensors, now you can have more variety. I can construct a two-index quantity Eij such that it is a product of the contravariant AI component multiplied by the covariant Bj component. And I can then define my E bar Lk as A bar L, B bar K. And if I do the same procedure, I will essentially get this. What it says is each index transforms as if it is an independent covariant or a contravariant index. For example, here I have I, which is covariant, is contravariant. So here I have L. So the L and I has bar by unbar, the way this has. Whereas the second index is a covariant index. Here it is unbar by bar, the way it is the covariant index. Is this clear? And so this is called a second rank mixed tensor. It is a mixture of covariant and contravariant. Is it clear?
Yes.
Yeah.
Okay.
Yes.
And one thing you should remember, when you are doing this, you have to be careful actually. You see, here I have very carefully kept this place empty and this place empty. So, strictly speaking, you cannot have both covariant and contravariant index at the same position. So, if suppose I have some quantity...
Unless they're symmetric, right? Like you can write it the same.
No. Be very careful on that. It's not symmetric. For being symmetric, both have to be covariant or both have to be contravariant. You see,
Yeah.
it's a very dicey thing, you know. See, for example, you take this one. This one will be, if I were to write EJI, this would mean AJBI, which is something very different from this. There is a thing about symmetric and antisymmetric I will come, but you have to be very careful because while doing symmetric, antisymmetric, in general, you can't mix up the covariant and contravariant. If there are two of them, both are covariant. Like for example, here, if I can interchange K and L, it will be symmetric. If I interchange with the minus sign, it's antisymmetric. But the problem is when you have a mixed thing up and down, then this interchange is a dicey thing. Harish?
Yeah, but I still feel like if they're equal, I can write it at the same spot, like AI on the top and I mean AI on top and J on the same without any space basically.
No, because okay, see, when I say symmetric, I should be able to interchange.
Yeah, yeah, I mean the same.
No, but
Same.
the problem is when you are interchanging, they have to be same kind of vectors, right? With which you have done. See, I mean,
No, yeah, that I understand. Like here we have decomposed the tensor into
see,
product of A
because
and
what
B,
is
but
happening is I'm not only exchanging A and B, but I'm
Mhm.
exchanging A contravariant by a covariant A and covariant B by a contravariant B. So some complicated thing I'm doing here.
Yeah, I understand that, but in terms of its matrix value, then if they
See,
are equal,
that's exactly what I'm saying.
hmm.
You know, tensor is much more than a mere matrix.
Yes, I understand that.
Yeah. And that is why one has to be very careful in this symmetry and antisymmetry thing. So you never talk about symmetry of a mixed tensor. See, formally I can write it. It's okay. But I mean, it doesn't carry that same impact or same meaning for a symmetric tensor, antisymmetric tensor. I mean, as a matrix being is one, that's fine. Okay. Hello.
Yeah, I get it, Trish.
Okay. I mean, all what I'm trying to say is, there are, you see, okay. So the covariant AI is a very different animal than contravariant AI. There is some relationship between them, which I will come to, but they are not
I
the same.
understand this is, but you're taking this explanation to the components, right? Like AI and BJ, because when we interchange the covariant and contravariant lose their meaning. But in general, for a tensor AIJ, when it is symmetric, we can write A.
No, I'll tell you why that misconception is there. That is because usually one comes across only Cartesian tensors.
Okay. Because even
Even
in the
when you go
initial
to,
pages of Lando, he writes this particular
that
line.
is because initial base of Landau, he is talking about flat spacetime.
Okay. Oh, yeah.
Okay.
It's
Okay. Yeah,
special,
yeah, yeah. See,
regime.
you go to the later chapters of gravitational thing, then he
I
will come up
never
with
got
all
that
this.
far.
Yeah. Okay. So I generally try to keep this distinction clear right from the word go. Okay.
All right. But the explanation with the components, I understood that. Like when we interchange and the meanings of covariant and
Yeah.
contravariant, they differ a lot there.
Yeah. Yeah. Actually, you can actually call something as AI, and there is something called lowering the index. But it is just some convention that they are both called by A. It is actually some other CI. Okay. I'll come to that.
All right.
So this is the mixed tensor. Now, let us, before I proceed with tensors, I want to again go back to why are tensors relevant? As I said, tensors have that property of preserving the form, and this is why it is. Now, if there are two physical quantities which are represented by second rank contravariant tensor, A bar ij and B bar ij. in some barred coordinate system. Then suppose in that coordinate system, I have A bar ij equal to B bar ij. So this is at LHS equal to RHS. When I go to a new system, which is unbarred, then as I was mentioning, this thing transforms in this form. Both the indices are contravariant. And B bar ij transforms and both are contravariant. So if suppose I write this A bar and B bar in terms of AB, I will get this, and this will cancel out, giving me AKL equal to BKL, which means that this thing about LHS prime equal to RHS prime, or LHS bar equal to RHS bar, implying LHS equal to RHS, is preserved. So in the new frame also the equation holds and the condition of strong equivalence principle holds. Is this clear?
Yes, yes.
Okay. Now, and this is all because since physical phenomena cannot depend on the coordinate system is used. And I was just mentioning that if a person falls from the 14th floor, the person dies, whether you describe it in polar coordinates or the Cartesian coordinates. It's a very morbid way of putting it, but it drives home the point that why, physical reality cannot change just because you use a different coordinate system. Okay. Now, okay, these are the things for which I could make the notes. So let me just continue. Now I will talk about higher order tensors, which is no big deal. For example, I have C, I, J, K. And I will say that when this has to be transformed, then I will say C bar A, B, C is equal to exactly the same way. X bar A by Xi, X bar B by Xj, X bar C by X K, C, J, I, J, K. So this is a third rank contravariant tensor. And you can understand that vectors are rank 1 tensors. What about scalars? Scalars had phi x equal to phi x prime. There are no del x bar by del x terms. So scalars are 0th rank tensors. Okay. And because there are none of these factors are there, that is why these scalars are invariant and the others thing vary. And once I have higher order tensor, I can mix and match. And this is where I want to be careful. I can have I, J, K, which is a mixed tensor where these are, there are 3 different indices. And the middle one is down. Now, here is where it's important. Now, I cannot write in general CJK because it will mean something else. Okay? Just like the case of ING. So, in fact, if you look at some of the older classic books on tensors, they will always write this as something like C, I, there will be a dot, J, a dot, K, a dot, which says that I am reserving this place for this I index and nothing will come here. And I will tell you why it is important. Okay? Now I can actually show a number of things. Product of tensor components are tensor components.
Sesh,
Huh.
these quantities are different, but they'll have the same transformation rule, right?
Yes, yes. Beautiful, beautiful, beautiful. So, the del x bar by del x factor remains same independent of where it occurs. You're absolutely right.
Oh, okay.
Okay. You're absolutely right. Whether it appears in second place or third place or whatever place, this transformation factor remains same.
Okay, okay.
Okay. Very nice. Very nice. Okay. Now, product of tensor components are tensor components. So if I take something like A, I, J, B, and B, like K, L, M, this can write it as a quantity which is I, J, B, K, L, M. Now you can ask, why can't I write it as C, K, L, M, I, J, B? I can. But it is just a convention. You have to follow the convention where I am, how I am placing them and follow it consistently. But what it means is, so if I act, so just like I said, just like AIBJ is a tensor, so it's a special case. Product of any tensor is a tensor of a higher rank. Okay. So if I have a tensor of rank n, okay, if a tensor of rank n multiplied by a tensor of rank m gives me a tensor of rank n plus m. I will just say one thing without contraction, and I will explain to you what is contraction soon. But as of now, just take this as this. Okay. Now I can say one thing, and I can add one thing. If suppose two of the indices are the same, for example, suppose I have Cij and Djm. Suppose I have two tensors. And I have a product which is E is equal to Cij Djm. Now J, since it is since it's equal, I am going to sum it over, which means J is a dummy index, which means E will depend only on I and M. It is equivalent to saying that I construct a quantity F, which is Cij DAM, low battery. Oh, I see. Okay. Okay. DAM. And what will this be? This will be FIJAM. Oh, again, that same problem has started off. I don't know. Oh, when I put it for charging, this happens. Oh, I see. Okay. Okay. So, okay. So I have F I J A M is equal to Cij DAM. Okay. So this is a tensor of rank 4. Mixed tensor. Now I do the following. Equate A and J and sum. Which means I have F I J J M and some more M, which means that this is actually a tensor which is CIM. Is this clear?
I have a question? So you're contracting a tensor like this.
Huh.
Is it equivalent to like integrating over
Yes, yes, yes.
given dimension?
It is the same as
marginalization.
Marginalization, exactly.
Okay.
That's correct. That's correct. Okay. Yeah.
Or it is just contracting with the Kronecker delta, right? Like identity density.
Okay. What Anirudh was saying is the continuum thing. You are saying the discrete one. That's
Discrete, yeah.
Yeah. Okay. So now, what is the moral of the story? Okay. So I'll just remove this. Now I'll modify this one. So if a product of tensor of rank n multiplied by tensor of rank m gives tensor of rank n plus m or n plus m minus 2 if 2 are contracted, or 4 are contracted, n plus m minus 4. Just make sure that should always be greater than 0 or greater than or equal to 0. You get the point?
Yes, yes.
Yeah. Anil, Ajil,
Yeah.
Anirudh.
Yeah, it's clear.
Yeah. Okay. So this is the thing. So this is what I call contraction. A particular example is if I have a tensor, a mixed tensor Aij, put I equal to j and sum over. So I have Aii. So whether I call it Aii or Ajj or Akk, it doesn't matter, dummy index. This has rank 0. And what is a rank 0 tensor?
Scalar.
It's a scalar and it's the trace.
Scalar. And this is called trace, which is what you see in matrices. So trace of a second rank mixed tensor is a scalar. In other words, if I go from one coordinate system to another, this tensor can change, but this trace will remain invariant.
I mean the magnitude of whatever it is.
Pardon?
Is it like, can you say it's like the magnitude of the given tensor because it's scalar?
No. You see, you forget that thing about magnitude and direction. That is
Okay.
I don't know whether you can call it a magnitude, depending on what you call magnitude, because magnitude is a very different connotation, which I will come to.
Yeah, magnitude is also invariant, right?
There are a lot of things which are invariant, but
I mean, if you're
also
talking about
invariant.
vectors and stuff, you rotate a
Yeah.
vector, the magnitude.
So the point is the following. So the point is here, you cannot talk about the magnitude as such.
Magnitude is more specific. So calling it an invariant would be a more broader definition.
Yeah, that's what I said. It's an invariant.
Okay.
It's an invariant.
Okay.
Okay. Fine. Now, of course, there are some standard things like matrices. I have a thing called symmetric tensors. And now we'll come to symmetric tensors. So I have TIK is equal to TKI. It is symmetric. TIK is equal to TKI, symmetric. This is a symmetric contravariant tensor. This is a symmetric covariant tensor. And I am specifically not saying anything like symmetric mixed tensor. Harish?
Yes, understood.
Yeah. Okay. So these are symmetric tensors. Similarly, I have TIK equal to minus TKI and TIK is equal to minus TKI. Antisymmetric, contravariant, antisymmetric, covariant. Now you can have higher order tensors which are symmetric in some quantities and asymmetric and antisymmetric in another. For example, if there is a tensor called a Riemann-Christoffel tensor, which we will come to, which has Rijkl. This is the interesting property that this is equal to minus Rijkl. It is equal to minus Rijlk, but this is equal to Rklij. So it is symmetric with respect to the first two pairs being interchanged, but antisymmetric when individual ones are exchanged within the pair. So the symmetric and this one is a very intricate structure in this. Okay. And there are some standard things which you can actually say that if a tensor equal to x times another tensor, then this will also be a tensor. Just like if x is equal to tensor into tensor, this is also a tensor. I mean, I will just leave it as an exercise. You can ask, ultimately what you do a coordinate transformation from x to x prime and see that this what happens. Okay, let us just see, for example, in this, let us see that. Suppose I have, say, Tij k is equal to Ck, say, Rij. And I know that this is a tensor and that this is a tensor which is a vector. I want to prove that this is a tensor. So what do? I do a coordinate transformation from x to x bar. So this will be del x I by del x bar A del x j by del x bar B del x bar C by del xk, because this is a covariant. So for k, it will be bar here unbarred, because I'm going from unbarred to barred. Okay. And this multiplied by T bar A, B, C should be equal to, this is covariant. So I have del X U by del X bar K into C bar U into R bar IJ. All right. Hey, is it okay?
Yes, yes.
I'm just so here I have to prove that Rij is a tensor, so I'm not using any transformation. Okay, so actually wait a minute. What I should do is, this just remains the same. So I just substituted for this in terms of the Baud coordinates. Okay. Right.
Shouldn't it be,
Pardon?
I think there's some mistake. Del X
What?
bar U by, on the right hand side, shouldn't it be del X bar U by del X K?
No, what I have done is, I have not transformed R. I have just transformed secant and written in terms of bar. That's all. Okay. I just substituted for T as T bar and C as C bar, and I have not done anything to R.
Okay.
Okay. Now,
that term, shouldn't it be del X bar U by del X K? Because on the left hand side, you've done the same thing for that.
del X. No. See, because this is covariant K, right?
Okay.
So unbar equal to unbar by bar. Oh, you are absolutely right. You're absolutely right. This should be the one. Absolutely right. Good. Okay. Okay. And using this, you can show that, oh, Anil has got logged out. Okay. Hi, Anil. Hello. I got logged out. Okay. Now you can show that Rij should be equal to del xi by del x bar, whatever, v, del xj by del x bar w, r bar vw. Using this, you can show that. Okay?
Yes, yes.
Okay. So just take it as an exercise.
Says I have a doubt in the previous Riemann-Christoffel tensor.
Ah.
So does an even number of switches always produce a symmetric description about that in this case? Like here, when we switch two indices, switch two type, i's and j's twice, we got a
Yes.
symmetric description, right? Like,
So what you are asking is, what happens when I put it like this? When I interchange these two?
yeah, that produces a
No.
negative sign.
No, that you cannot say. There is nothing about antisymmetry or symmetry there. It just produces a new tensor.
No. I think my question was like, like in the first two examples, you interchanged i's and k's only once. Basically, there was only one effective switch there.
Yes.
But when the second one, you switched it twice. So, negative.
No. You see, I can have an tensor like Cijk, which is equal to minus Cjik, but is equal to Cikj.
That's what I'm asking.
So
Like
this
in
can happen.
Yeah. So for the fourth order Riemann-Christoffel tensor, this is happening twice for an even number.
No, it is not any even number. I can't do anything with J and K, for example. If I do IJ and I do KL, you're right.
Okay, it is index specific also.
Yeah. So you can't mix up the first two and second two. Either
Okay.
you take them M block and change it, or within them. You can't just partially change across them. You can change it, you'll get some tensor. It doesn't have any antisymmetry or symmetry property. That's all I'm saying.
All right.
Okay.
And we'll be studying that, right? This Riemann Christopher tensor.
Sorry, what is it?
Will we be studying this particular Riemann's Christopher tensor?
Oh my God, that is going to be the main thing.
No, does it the Christopher symbols, right? Like, do they correlate with each other?
No. This I'm just calling it Riemann-Christoffel tensor. I'm not using any property. That all will come in detail. I'm giving as an example where it doesn't have to be completely symmetric or completely antisymmetric. It can be antisymmetric in some index and symmetric in another index.
Yeah, I understood that it was an example, but I was just curious to ask that.
Sorry, so no, I didn't understand your question.
Like, I understood that it was an example, but I was just curious to ask that before.
Oh, yeah. Our main work is going to be in Riemann-Christoffel tensor, because Riemann-Christoffel tensor is ultimately the object which encodes the effect of gravity.
All right.
Yes.
Like this will come in the field equations or in the
Oh,
geodesy.
yeah. No. Soon you'll be coming. Once you do, here I'm still doing tensor algebra. When I do tensor calculus, from there it will come.
Yes.
Yeah.
Yeah, I have one question. Like, whenever we use same three indices, like you
Yes.
can use two indices, okay? But
Uh,
when you use same three indices, you run into trouble. But I don't
yes.
understand why it happens.
No, it's not why
Is
it
there any
happens.
logic?
No, there is no logic for it. It is just that, I mean, there are very rare situations where there are three indices which are equal. I mean, it is just that, it is like this, when you have dot product, you don't have a dot product of three vectors.
Mm-hmm. Mm-hmm.
It is the same thing, because when you have dot product two vectors, there are only two indices which are there. Right? Anil.
Uh-huh.
Okay. I mean, like, for example, I can always take Jabardasti, A, B, C, A, I, B, I, C, I, and then add it. I mean, probably you never come across in physics that kind of a thing. Maybe it comes very rarely, but so rare that it's specifically mentioned in that case. Anil?
I understand. Okay.
Yeah. Okay, I think we'll stop here, because I think it is, I am sort of losing steam, because I am one of those by now who will be getting ready to go to sleep. Chalo. Is that okay? Okay. Chalo.
Yes, it's fine.
Good
Bye.
night.
Thank you.
Good night,
Bye.
Jason.
Good night.
Good night, Sesh.
Good night.